Hello, good morning, teacher again. I'm Nuththawat and my group mate is Patanin and Suprak. Today we are going to be presenting you about our celestial sphere on the assignment 3. Okay, first of all, as you can see here, the blue lines, a blue line is the celestial equator. However, the yellow line here is the ecliptic. Okay, next let's talk about the vernal equinox. So the day and the night times are approximately equal in the length, which means they are both 12 hours. And for the sunrise and sunset, so the sun rises exactly in the east and sets exactly in the west, because the sun position is directly above the equator. Okay, next is going to be summer solstice. The summer solstice daytime and nighttime is pretty different. For the daytime, it has the longest day in the year for the North Hemisphere, and it will have the shortest night. And this is reversed in the Southern Hemisphere, which means the daytime will be the shortest for the South Hemisphere, and the nighttime will be the longest one. The sun will rise at the northeast and set at the northwest. Okay, next is going to be the autumnal equinox. The daytime and the nighttime for this particular point is exactly the same as vernal equinox. So it has 12 hours for the daytime and also the nighttime. And the sunrise and sunsets is also the same. The sun rises exactly in the east and also sets exactly in the west for both hemispheres. And lastly, it's going to be the winter solstice right here. So for the northern hemisphere, the nighttime will be the longest one and the daytime will be the shortest. While the southern hemisphere, the nighttime will be the shortest and the daytime will be the longest one. The sun will rise at the southeast and set at the southwest. And here are some more information. So the vernal equinox will be located at the 0-hour right ascension and 0-degree declination. For the summer solstice, the right ascension will be 6 hours and the declination will be around 23.5 degrees up north. And the autumnal solstice, the declination, the right ascension will be 12 hours and the declination will be 0. And lastly, the winter solstice, the right ascension will be around 18 hours and the declination will be around negative 23.5 degrees. And the other three questions, Patanin will cover. Thank you very much.
Next, let's move from the model to something more details. Let's assume this circle is an Earth. Okay. So an Earth has its own rotational axis, and up above there is the North Pole. Just above the North Pole is called North Celestial Pole, or NCP. And just below the South Pole is called South Celestial Pole, or SCP. These 2 points, NCP and SCP, are aligned on one sphere called celestial sphere. And that line, that purple line, is called the celestial equator, which could be called also the reference plane. And this one line is a ecliptic. As we know from the model, ecliptic is the path that suns move along. And the point that the celestial equator and this ecliptic meet each other, the first one is called the vernal equinox, which is the reference point. So why do we call these two things the reference plane and reference point? Let's maybe clear something out right here and move something up here. So there are 2 values that astronomers want to consider. The first value is the right ascension, which has in units in hours, and the starting point that astronomers count as a 0 hours is at the reference point or the vernal equinox right over here, and when it's go toward the right, it's going to be 2 hours, 4 hours, 6 hours, and up until 18 hours, 20 hours, and 22 hours, and back to 0 hours at the reference point. Next is about the reference plane. It's called the declination. So at the reference plane, declination would be 0 degrees. And when it's go outward to the north, it's going to be increasing from into 30, 60, and at the north celestial pole, it's going to be 90 degrees. And when it's lower down to the south, it's going to be minus 30 degree, minus 60 degree, and up and down towards minus 90 degrees at the south celestial pole. You might wonder what are the use of these two values. So these two values are the value that's used to tell the position of the stars in the sky, and it might be, you might think that it's this to measure or maybe calculate for this value, it might be hard for us, an observer from the earth that have no utensil for helping us for the measurement methods. But actually, to identify the declination from an observer, it's not that hard. So let me tell you something first. So first, let's assume this green guy is in the north hemisphere, and these are axes, the north, east, south, and west. And if you look toward the north and look up with a degree theta, that 1 degree would which is equal to his latitude. At that point, it would be an NCP or North Celestial Sphere, and just directly backward from the North Celestial Sphere, that one gonna be the South Celestial Sphere. It's gonna be under his ground, but yes, that point is gonna be the South Celestial Sphere. And so how do it? So let's assume that we are a guy that stands in the North Hemisphere and looking through the stars. So what we're going to do is we're going to look through the north and find that one star called Polaris. So that one star is going to be our approximation of the NCP or North Celestial Pole. So if you want to know the declination of the stars that is right above the Polaris, that one star would have the declination equal to the degree that that one star do with the Polaris and with us, the green man right there. That theta would be the declination, and every stars that form a circle to that stars while having a Polaris or NCP as that circle center would have the same declination with that star. So so we know that theta are going to be the declination, but how to find the theta? Maybe some people would say it would hard for finding that one theta, but actually it's so simple. You can use the most simple thing, the things that every human, like most of human would have, is our hands. So this is a diagram that shows if how many degrees that it would form. So this is just an approximation, but it would be quite accurate enough for us to just measure simple declination. So first thing we have to do is we're going to hold our hand at our arm length and close one eye. So just choose to close one eye and do the hand signals as shown in the in this picture. So if the star is like this, like from our thumb to our at this point, it's going to be 25 degrees from each other. Like if one star, we assume Polaris is right here, and that one star, the purple one, is right here, and we just close one eye and hold our hand at our arm length. this one is going to be 25 degrees declination. Yeah, and other symbols we can find it right here. Yep. So let's do our first examples. So and a stars and it's just above that, and MCP is just down right down a stars. So if that one is our fixed size, it's going to be 10 degrees, right? And this would be the declination. So what about the south hemispheres, if you may ask? So there would be A stars that have the position of like close to the SCP or south hemispheres, but it would be much less bright, like, so it's harder to find. So basically we're going to do the degrees from the ground as an latitude from in the direction of directly south. So that would be an SCP or south celestial sphere. And so if you want to know the declination of that stars, maybe the purple one again, but with a different place. So first we're going to draw the circle, our imaginary circle that across the south celestial sphere, south celestial pole, and let that one point, the south celestial pole, again be the center of that circle. And we're going to measure it the point just right above the south celestial pole, and still on that circle, our imaginary circle. And yes, the declination would equal to the angle measured from angle measured from the south celestial pole. So use the same method, hold our hand as our arm length and close one eye and see how many degrees that would be far from, and that one would be the declination of that one purple star. So there are some additional informations. So if we just look through the, maybe if we are in north, we look through the north hemisphere, and we look through the north direction, there would be a north celestial pole up there, and there will be a group of stars right there that it would circulate around the north celestial pole, or maybe circulate around the south celestial pole again and again, and it won't be off the ground, since the lowest point is above the ground. So so if it's going to be it's north celestial pole, the star would circulate like this, and if it's south celestial pole, it would circulate backwards right there, and it's going to be circulate all day, and it won't off the ground. So those stars are called circumpolar stars, and there'll be like one thing that we want to calculate is the degree of the stars, like what is the declination of the stars that would make the stars not get off the ground. So this degree would be the degree that equal to the degree from the ground toward the north celestial pole. So this one degree is that one blue theta, which that degree would equal to the green theta right there, and the star within this range, this declination, it won't get off the ground, and they are called circumpolar stars. And yeah, that's all for this video. Thank you everyone for your attention.